Okay, hello, welcome. Here's another recording for our For You, continuing our discussion of dynamics. We're going into chapter 2. This is based off like the textbook, which you guys don't have, I suppose. However, this is lesson number 5, forces. It's a new sort of section because you notice that we're changing gears just a little bit. So instead of talking about kinematics, right? Kinematics is the stuff we were doing before. That's like velocity, accelerations, and displacements. Now we're going to start talking about forces acting on objects as well as how to draw free body diagrams, or rather to remind ourselves how to draw free body diagrams. And then we can start seeing that we can incorporate our discussion of forces, which will be a little bit of review from last time, just like free body diagrams, but we can incorporate them together with our exploration of kinematics to make our new unit or a new study of dynamics, right? So kinematics ignores the forces that are acting on the object. It solely looks at the velocities and accelerations, whereas dynamics focuses on motion while accounting for forces. So let's get into discussion of forces. So a reminder of a couple of things. Remember that a force, I guess we'll talk about it in a second. So we have these different formulations down here that we have F net equals the sum of all the forces acting on the object, also shown with this other equation here, F net equals this, remembering that this expression here and this expression here are the same thing. This is, let me do it in maybe yellow, if it's not too dark. This is Newton's first law. This is also called the law of inertia. This is the mathematical formulation of it, right? So this is like the object in motion tends to stay in motion, which is saying that if there's no force acting on an object, then it's just going to continue just moving in the exact same direction that it was going in originally, right? So if we picture ourselves in our space lab, that means that if there's no gravity, if we're in a region where there's no gravity or anything, if there's a ball traveling in a particular direction, if there's no forces acting on it, that ball is going to continue moving in that direction forever, right? Until it encounters another force. So that's Newton's first law. This is the law of inertia. We're going to talk about inertia a lot more, so we don't have to get into too much of a description of it here, but it is worth repeating. Inertia is a property of matter, and it's related to forces. But the inertia of something is it is what we just described, right? If that object doesn't experience any other forces, what's keeping it moving is this concept of inertia, right? Because it seems very counterintuitive that if I let a ball go in space with no other forces, that it continues to move. Our conception of it seems to think that there should always be a force acting on it that's causing the movement, right? That's not always the case. And if there's no forces acting on it, but we still see movement, that's due to inertia. While we're on this topic, I think it is worth mentioning, I'm just going to switch this color back to red. I like that yellow, but we'll do the red. This is also worth mentioning that there's two types of equilibrium. There is what's called static equilibrium, and static equilibrium is the net force on the object is 0, and the object, more space, is not moving. This is what we assume would happen, right? And so just bears repeating again, it's not what you know, it's not what you don't know in physics, it is what you know. We bring a lot of our preconceived notions of how we think things should move based off our everyday experience, but the simple way to look at it, right, again, separating all of the complicated forces that are in the day-to-day, like gravity, wind resistance, those things all play a factor. And so the situations that we see in our day-to-day are actually a lot more complicated than they really are if we were to, again, go to our space lab and have no forces. Like if we could control all the forces of it, then these things would start behaving in very strange ways, or it might, or rather seemingly counterintuitive ways. So we have to build a new understanding for this. So the static equilibrium is the one that you assume, but then here's another one that is a bit strange to picture, is that we have dynamic equilibrium. The net force on object is 0. I should put an is also 0, right? And object is moving. So that seems very counterintuitive. If there's no net force acting on the object, then how can it still be moving? The key word here is net force. We're calling that we can have multiple forces acting on an object, but if all the forces are balanced, then the net force is 0. We'll explore this more as we get through the note, but here I want to just point out these definitions and notice the term equilibrium, right? Equilibrium, this is balance. Okay, so that's what this term equilibrium means. It's implying a balance. Static, something that is static is not moving, something that is dynamic is moving, right? So even though we can have both cases of equilibrium where the net force is 0, but we have two conditions, right? The object could be moving or the object could not be moving. Those are all consequences of Newton's first law, this law of inertia. Okay, so we describe that mathematically as F net equals the sum of all of these forces. Now let's take a look at a formulation for what we call Newton's second law, this one right here. Which is the description of what a force is. A little bit tricky because you notice that the first law assumes you know what a force is, whereas the second law really defines it, right? Newton's second law states that the net force on a thing, or just the force on a thing, is that thing's mass multiplied by its acceleration, right? Or we can rearrange that formula to define that an acceleration is caused by a force divided by the mass of the object that's moving. So if something is moving, we take the ratio of the force applied on it divided by its mass, right? The ratio of the force to mass of that object, and then that ratio is what the acceleration is. So in order for something to accelerate, it needs to have a force acting on it, right? So if F net equals 0, then the acceleration is also 0. That's key. So if there's no forces acting on a thing, then it can't be accelerating. Again, seems counterintuitive. You might say, but sir, how can it move if there's no acceleration? Anything can move without acceleration, right? Your car can move without acceleration. Again, now so in our space lab, we have a car on a road that's driving. You put on the cruise control of the car. The car is no longer accelerating, but it maintains its velocity. Now, this doesn't happen in real life because there's friction acting on the car, there's air resistance acting on the car, there's gravity acting on the car. Your car constantly needs to accelerate in order to maintain its speed. But if we were in space with no forces acting on it, and our car could magically drive in space somewhere, or like a rocket ship or whatever, we would accelerate up to a speed that we wanted to get to, and we could stop accelerating. So we can turn our engines off in space. So our rocket ship could accelerate. We could turn our engines off once we got to 100 kilometers an hour relative to whatever. And then we would just keep going at that speed until we turned our engines on and wanted to go faster, or we turned our engines on the other way and wanted to slow down. I can't remember if we're going to talk about it yet. So while we're talking about Newton's laws, let me just throw in the third law. And let me rather include in yellow, because my yellow is my first law, right? So I just want to put that in yellow there. And then why don't we put the third law in blue, remember that. I can't remember if when we talk about it, so I'm just going to say it here. Newton's third law. So this is all review, or at least it should be, is that the force of, let's say, object 1 on 2, so I have two objects. Let's say that I have a ball, I don't know, and like I have like a square, right? Just so that they're easy to tell the difference. Object 1, object 2. And then they're exerting a force on each other somehow. That the force that 1 exerts on 2, right, is going to be equal but opposite to the force that 2 exerts on object 1. And these are vectors, right? So we have two forces that are opposed. We have force 1 on 2 over here, and then we have the force of 2 on 1, right? They have the exact same value, but they're just opposite in direction. So the force on, you can see that 1 pushes 2 to the right, but then 2 immediately pushes back on number 1 to the left, right? That happens with all objects, and that's Newton's third law. This one might be the hard, other than the inertia, the law of inertia, I think the third law is probably the hardest one to get your head around. It's easy, mathematically it's the easiest, but conceptually it's actually quite difficult. So remember that when you do a push-up, right, the reason that you can do a push-up is that you push, like doing a push-up on the ground, right? Here's me doing push-ups, right? Doing a push-up off the ground. This is me sweating because I'm out of breath and I'm old. I push down on the ground, right? So my arms, I don't know how to write this. My arms exert a force downward, right? So my arms kind of push down, and that's me on the ground, right? I push down on the ground. But now here's the thing: I'm exerting a force on the ground. That tells me that that there's a force on a mass. It should be accelerating, right? The ground should be moving down, but it doesn't, because it also pushes back up on me, right? So that happens whenever objects are in contact with each other. They always exert this force, and they end up being balanced. So we need to find some way where I can overcome, right? Where the applied force that I push on something. So if I wanted to tip over like a coat rack or something, what I could do is I would push on it, right? And then the coat rack is also pushing back on me. But the thing is that if I could cause the coat rack to become unbalanced, I could now unbalance its forces. So then gravity could do some work. So if you just sort of tip something very gently, then the force, like the magnitude is going to be the same, because my arms, my finger won't go through the coat rack, right? Whatever, if an object that I push on and I can move, my hand doesn't go through it, right? My hand, there's resistance to it. So when I touch a thing, my hand stays my hand and the thing stays its thing. Like we don't combine each other, right? Because of these forces. This is a result of the electrons, right? So if we sort of like zoom in on these two objects that are in contact, we have the atoms in the surface of one of the one object repel the electrons in the surface of the other one, right? So that's what's happening. These electrons are pushing against each other as they come in contact. So this electrostatic repulsion is what causes Newton's third law, which is pretty interesting. But Newton didn't have any idea, or at least didn't have our understanding of atoms that we do now. Okay, so I just wanted to point those out. So those are our different laws. Okay, let's look at some examples. Oh, and then lastly, just to talk about quick, I guess, a new color. We'll do pink, and then here is our expression for the coefficient of friction, right? I can do a pink, purple, where this is the expression for coefficient of friction. Let's start going through an example. Okay, you're holding a basketball. The force of gravity on the ball is 16 newtons down, okay? What is the net force on the ball while held stationary in your hand? So our diagram here is that we have the basketball there, and let's imagine that this is my hand here in contact. There's a force of gravity on the basketball pulling it down. So we have a downward force, which is gravity. What's the net force on the ball while held stationary in your hand? So even though gravity is the only force acting on it, there has to be something else because it's not moving downward, right? Newton's laws say that if there's a force acting on it, it should move in that direction. But obviously the basketball doesn't move downwards when it's on my hand or it's on a surface, so something else has to be going on. So let's take a look. So the net force is just the sum of all the forces that are acting on a thing, and we can balance our force of gravity with what's called the normal force, which is the opposition to gravity, which is contact. Let me see. And let me just define the normal force, where F sub n is the normal force, and it's a contact force. So that means that in order for a normal force to exist, an object has to be in contact with something else, right? And then the normal force always acts perpendicular to a surface. I'm going to move that up a bit so that they're different. So in this case, the normal force will act upward, just by definition. So the net force that will be acting on it, we can define our net force equation will be then the normal acting up, and we add that to the gravity that acts down. So we call that our net force. And then we assign some directions. We say that up is positive, and we can say that down is negative. So then what we can do here is then our F net will end up becoming a subtraction, the normal force minus the force of gravity, because gravity is going down in our negative direction. Now, another thing that we can assume is that since it's stationary, what that tells us is that the net force is 0. Therefore, 0 equals the normal force minus the force of gravity. Doing a quick rearranging, we can see that the normal force is equal to the force of gravity. We have already taken this into our direction into account. So the normal force points up, the gravity force points down. So they're going to be equal in magnitude to each other, and their directions are obviously opposite. Oh, on the ball, so move your hands. I think I'm jumping ahead here. I think all I needed to say was that the net force was 0. I'm so sorry. I'm getting ahead because it wasn't even asking me for the normal. But it's stationary, so we know that the net force is 0. I'm going to get to the normal force in a second. I think I jumped the gun a little bit. Sorry. Anyways, it's fine for now, but the net force is just 0 because it's stationary. So now, neglecting air resistance, find the net force acting on the ball if you suddenly remove your hands. So in our new situation, we see that the ball is here. There's nothing acting on it. There's no more normal force acting on it. So our force of gravity just acts downward. So then that tells us that the net force is equal to the force of gravity. And the force of gravity, we were told, is 16 newtons. So that means that the net force is equal to 16 newtons down. So this is the immediate moment after we take our hand away, right? It's immediately after our hand is removed. Okay, if we push the ball with a force of 12 newtons to the right, calculate the net force on the ball. Let's assume that the ball is resting on a surface. I think. Let me just go back here and make sure I do this right. Yeah. Yeah. Oh, yeah. That's it. Thank you. We have to ignore that. That's the little fun part about this equation. I can still include this. I'll leave this in. That the F net is equal to the normal plus gravity. And we'll see another example there, but ultimately the F net is 0. Okay, so let's just imagine that the free body diagram just looks like this. There's gravity that pulls the guy down, and then we are pushing it to the right with a force of 12 newtons, which is an applied force. And you know what? Let's actually... this is the good time to start talking about this. So I've just been using dots. That's totally fine. But you'll find that sometimes it's convenient to draw these objects as squares. And in our diagram, so even though it's a ball, I'm just going to draw it as a square because it's not art class. And we are pushing it, right? So for the free body diagrams, the force that we're applying comes from us on the left side of this object, right? So we're pushing it there. But the correct free body diagram, if you notice that if we drew it like this with an arrow pointing like that, that doesn't really look very good, right? So our free body diagrams, by convention, all the forces come from the center, and then they go on the side that corresponds with the direction. So the applied force here looks like this, right? So this force is the applied force. It's on the right-hand side because that's where that force is pointing, if that makes sense. This is just a bit of it might be a bit of a mental jump to do there, so that's why I bring it up. Hopefully I'm not confusing you, but even though you are pushing it on the left-hand side, the force is going to the right, so we can draw the force starting from the right because it's equivalent. It doesn't matter where we put our vector. I think that just to make things even, we have all of our forces originating from the center of the object, right? So we can even extend this to the center of it. But you don't always have to show that goes in the center. You can just draw it from the surface of our square or circle, whatever you want to do. And then we have our gravity, which acts also from the center, which pulls it down. So let's find the net force on the ball now. And then we are going to just ignore the normal force for now because we're in our space lab. So the net force is the sum of both forces acting on it, right? Which is the applied force and the force of gravity. But then we notice something interesting is that they are perpendicular to each other. So they're not going in the same, they're not in the same plane. So things become a little bit tricky. And our ball, this is the same ball from our example. So our force of gravity is still 16 newtons, right? But we have this new applied force here. So what we can do is we can say that, okay, we know that the applied force is 12 newtons, and that goes to the right. And the force of gravity is going to be the same as above, which is 16 newtons down. Come on. Where sorry, gets so messy so quick, doesn't it? And I just want to say that a newton, or rather 1 newton, is equal to 1 kilogram meter per second squared. So a funny unit for the newton, so obviously kilogram meters per second squared is kind of strange, right? Another way of looking at this is you could say that this is kilogram meters per second, right? This thing per second. So a mass times a speed per second is what we're talking about, right? That's what an acceleration is. It's how fast something goes per second. So we're just combining those units there. That's why the meters per second squared, it seems a bit strange. But that's the definition of our unit for a Newton. Just that should be a reminder, but I wanted to put it in here so that you could remember, because I know I get caught up with my units a lot, and I can't remember which ones are which, but you do it so often that you eventually get used to plugging them all in. So what did we do? In the previous example, in the previous chapter, when we had forces or vectors that were perpendicular to each other, we just created a triangle. So what we're looking for here is the net force. So applied force goes there, gravity goes down. The net force will be somewhere down the middle of it, right? That's where the net force will end up. If we want to find out what that is, we can just redraw our triangle and however we want to do it. Redraw the triangle, we could say that the applied force is here, but then we can put the force of gravity. We could draw them tip to tail, like we're supposed to do. And then our net force will be the sum of those two guys. So here's our vector addition again, right? So you notice that the net force is adding them together. That comes from vector addition. As I get rid of some of this. So my triangle looks like just this. It's a right angle triangle. And we can see that the magnitude of, we can use the magnitude of these two forces with our Pythagorean theorem to find the hypotenuse, which is our F net. So we can say that the net force, I'll do it in different color so it stands out. So the net force on something, so the net force squared will be equal to the magnitude of A, the applied force squared, as well as the force of gravity squared, right? Just from Pythagorean theorem from our triangle. Just to sort of show, so because I'm getting kind of messy. So that means that F net, the magnitude of F net, will be equal to 12 squared plus negative 16 squared, because 16 points down, right? We established that down was our negative direction, but we just square root those squares. Oh, and I don't have my calculator, so let me just look back because I already did this. Negative 16, 20, and then 37. So that equals 20 newtons, but we need a direction. So just sort of cutting this off down here. We need to establish a direction, so we need to figure out where our direction is. And again, sorry, I don't have my calculator. So the x over y works. Why did I draw it like that? Anyways, so we can use our ratios to find this angle in here. I don't know why I found that other angle, but let's see if this works. So then that means that our measure of theta, let's do it in green, or rather the tangent of theta, will be equal to the opposite over the adjacent. So in this case, the opposite is the force of gravity, and then the adjacent is the applied force, right? The y over the x. So that means that theta will be equal to the tan inverse of gravity, which was 16, over 12. Which I can use my phone. So 16 divided by 12 equals that. Where's my tan inverse? My shift, tan inverse. So that gives me 53.13 degrees. Let's just call that 53 degrees. So my net force is 20 newtons, right 53 degrees down. We did all that because the forces were perpendicular. Okay? Let's see what happens if we push the ball with a force of 26 newtons up 45 degrees right. Let's find the net force on the ball in that situation. So in that situation, we are pushing it with not perpendicular to the gravity. We're at a bit of an angle. So here is our ball, our square ball. But our force now goes like somewhere up here, right? Diagonal. It's up and to the right. Our gravity still goes down. This is our new applied force, F sub A, right? That's a little a because it's an applied force. And it is 45 degrees up. I'm sorry. It's up 45 degrees right. It'll be, the angle is actually not there. Oops. Up 45 degrees right is up here. Right? I didn't draw this very well, but it's this 45 degrees, right? Up and to the right. Find the net force on the ball. So we know, again, our net force is equal to the applied force plus this force of gravity. But what we'll need to do is we'll need to separate our applied force into its components, right? And we'll just add our components, all of the components in the same direction together, and then whatever is left over, we can then use with our components in the other direction, and then again, our Pythagorean theorem to help find. So drawing a triangle for the applied force, on this side now, we see that the applied force goes up and to the right, and then its components are, actually, let me move this because the angle is to the vertical. So we will need a y component going up here, and then, that's too big, and then an x component going there. Let me redraw those. Y component up about here, x component going there. Angle in between these is 45. Now, I usually do it from the horizontal, but the question told us from the vertical, so let's just do that. You could always just flip it, right? 90 minus 45 to do the horizontal if you wanted, but I'll show you another way just to sort of keep life interesting. So this is the component of the applied force in the y direction, and this is the component of the applied force in the x direction. Our triangle of applied force is like this. So let's find our components, and then we can add up everything in their respective directions. So the components of A are components. So the, I can do these in another color. FAY is going to be equal then to the, this is the cosine ratio because our y is adjacent. So that will be the applied force scaled by this, cosine theta. And then the force that's applied acting in the x direction will be equal to the applied force modified by the sine of the theta. So these are both applied forces, but we're just splitting up the total thing there. Okay, so we have expressions for each of those. then what we're going to want, then what we do is we can use Newton's law, Newton's first law in the two directions. So the nifty thing is that we can now change our F net equation. We can get to F net in the y direction will be the sum of all the y forces. So taking a look at our diagram now, if I can draw my components, or drawing my components on without making it too messy, and maybe I'll use red. The y component goes up like that, and then our x component goes over there. You can see that in the y direction there's gravity, and then there's the y applied force, and then in the x direction there's only the applied force. Because, are we also ignoring normal? Let me see what I did before. Yeah, let's keep ignoring the normal force just to make our lives easier. So we're going to continue ignoring the normal. Let me make a point of that. So we're continuing to ignore the normal force. So the F net in the y direction is now the sum of the applied force in the y direction, and we'll add that to the force of gravity, which is also in y. And then our net force in the x direction is simply the only thing that's pushing it in the x is that applied force. So the applied force is going up and to the right. So we have, right, so there's two sort of components. So we can split our F net equation into these two guys. We can then find the components of our net force and then use Pythagorean theorem to find the net force. Okay, so one step at a time. Why don't we do the, let's do it, I can do it in blue and orange. So why don't we do F net y? So F net y, if I can save space, where's a good place to go? Down here? Or let's just do F net x, I'm sorry, because that will be simplest. F net x is just equal to FAX, right? Like we had above. But that FAX we can see is equal to FA sine theta. FA was 26, and then the sine of 45. I don't know this, sine, so 45 sine is that times 26, so that gives us 18.3848, and that's newtons. We'll leave that now. We can round later. Now, let's do F net y. I'm going to do it up here because we need a bit more space. F net in the y is equal to FA cosine theta minus FG. Gravity goes down, the y component of the applied force goes up. So what do we get? FA is 26 cosine of 45 minus the value that we were told. The gravity was 16, right? Yeah, 16. So that stays the same. So what do we get? So we will do 45, the cosine times 26 equals that, and we'll subtract 16 from it. So the net force in the y direction is only 2.3848. That's also newtons. You can see that the gravity diminishes the y force, right? So the y force becomes a lot smaller, but since there's nothing opposing the net force in the x, it's like a bigger, or it's kind of closer to these other values. So we have our values for each of these net forces. Then we can just use the fact that what we're looking for here to draw yet another triangle is our net force is pointing to the right, and it's just a little bit above 0, right? So we can use a Pythagorean theorem. I can do that in orange. So the net force, let's maybe I space over here. So then F net, so there's the total, like the net we were looking for is going to be equal to its components, right? F net x squared plus F net y squared. If we look at how all of our net forces are going. Then we can just plug in our values. So this means that this is going to be equal to the F net x 18 point, so this is 18.3848, and that's squared. We're going to add that to 2.3848. That's also squared, and then we square root those. Okay, so 18.3848, square that, add that, wait, hang on a second. Add that to, oh boy, 2.3848 squared equals, yeah, okay, good. I think that works. And then square root. So our F net should be equal to 18.5388 newtons. This was just my intermediate in case I lost my calc. Now we also need a direction on this. So the tangent of our angle theta, I think I need to draw this, don't I? I do need to draw this. So our F net is going to be these two things. Yeah. So our net y, it goes up. It has some positive value, not very big, and then it has an 18. So it sort of looks like this. It's kind of small, right? This one's kind of long. So it's pointing sort of this way, right, is our F net. And then why don't we look for this angle here? We'll do that theta. So then that means that the y is going to be our y is going to be adjacent. So it's opposite over adjacent, so it's our x 18, let's do it same color. 18.3848 divided by 2.3848. So then that means our theta is 18.3848 divided by 2.3848 equals that. And then I want to do the inverse tangent of that. 82.609, which we're just going to call 83 degrees. So the net force, as long as I'm not still hang on, we got a round now. Take a look at our sig figs. I think everything's going to be 2. We were given 16 only has 2, and then the 12 and stuff. So as well as this 26. So we'll just have it with 2 significant figures, so that's going to be 19. 19 newtons. This is up 83 degrees right is the net force for that then. So we can see, using all of our forces, and this is quite the note. Let me separate some of this. To sort of help you with the separation of where the questions are and what is the question and what sort of isn't. Okay, so there's the first example for our net forces. You notice that there's a lot going on. It seems very complicated, but it's the same thing sort of repeated over and over, right? And it's also building on the stuff we already talked about with our components from last time with it. Okay, so we'll go to example 2 in just a bit.